Yeah. You can turn on your video if you want, but I think it's fine. Oh, yeah, then that should be good.
Not sure I will. Okay.
You can do full screen.
Oh, yeah. Okay.
Great.
Yeah, okay.
All right.
Cool.
Well, it's a pleasure then to introduce Quentin Bonnefoy. Quentin was a PhD student in Paris with Emilien Dudas at the École Polytechnique, and then after that, he was a postdoc in Daisy, and then went to Berkeley, where he's now a postdoc there, but not for long because he has a permanent position back in France. He'll be going to France in Strasbourg, is that right? Next year. And so today he's going to tell us about a colorful mirror solution to strong CP.
Thank you. Okay, thanks everyone for being here. Thanks for the invitation. I'm very happy to discover University of Minnesota. It's my first time. Yeah, so I'll be discussing this colorful mirror solution to the strong CP problem. So this is based on that paper, which appeared earlier this year with Lawrence Hall, Claudio Manzari, and Christiane Scherb, last two being also postdocs at Berkeley. And it's also, towards the end, I'll also discuss some aspects of cosmology of that model, which we are still working on with the same people, and Amara McCoon, who's a PhD student, half between Santa Barbara and Berkeley. And of course, feel free to interrupt whenever I have any question. Yeah, I thought of starting with a review of what the short review of what the strong CP problem is. I think for some of you in the audience that would not be necessary, but okay, I'll apologize for those of you who know that very well. So the strong CP problem is associated with the different CP odd sources in the star model Lagrangian. So this story is both extremely successful and extremely disappointing in the star model. And the successful part of the story has to do with the quark matrices. So if you're looking for CP odd quantities in the star model, you're going to look first for them in the quark sector, where you have many complex parameters in the quark matrices. Of course, we know that not all of them are physical, and that we should, first of all, use the freedom of redefining some of these parameters away. Oh, yeah. Yeah, so we are free to redefine some of those parameters away using those unitary transformations of the different quarks. So once you do this, you find that in the star model, you're left with only one physical phase in the classical theory of the star model, let's say. So that only applies when you have three generations matter, which is the key insight of Kobayashi and Maskawa in the early 70s. If you're not a big fan of performing unitary transformations, you can also rely on objects which have that form, which have the property of being independent on whichever of these transformations you're performing. So the same statement can be phrased as saying that in the star model, there's only one object that is CP odd that you can form out of those Yukawa matrices, and that starts only being non-vanishing when you have three generations. So that goes under the name of the Yarskog invariant. So that part of the story is what, for instance, is sufficient to predict what we observe in terms of k-on oscillations, for instance, or CP violation in k-on decays. But that's not all the CP violation that you would expect in the star model. There's another parameter that happens to violate CP, which has to do, which is the one that multiplies the QCD topological density. So that operator thing that I'll also refer to as GGDO a lot in what follows. So because of the epsilon tensor, that operator breaks both P and CP. And because of the quantum anomalies that you have when you start performing those chiral rotations of the different fields, that parameter is going to receive some corrections that come from the quark masses. So if you play the same game, trying to form objects which are flavor invariant, so which don't depend on the choice you make for this kind of flavor rotations, you can form a second object in the star model that has that expression, which is a combination of the naive pair parameter that you start from the Lagrangian and some contribution that comes from the quark matrices. That is the contribution that quantum anomalies will generate once you play this game of removing the physical parameters in the Yukawa matrices. So a priori in the star model, you have these two independent sources of CP violation, one which we've observed to great accuracy, and which is one of the great successes of the star model, and the other ones which we haven't seen at all. And that second part is what we call the strong CP problem. To make it a bit more quantitative, I should first say that there's a reason why it's hard to probe that thing, so that I call the theta angle, so that parameter, because unlike the phase in the CKM matrix, the operator it multiplies is completely invisible in perturbation theory. So it's a total space-time derivative. And for that reason, it does not contribute to any perturbative like scattering amplitude or cross-section. And to see its effect, you have to rely on non-perturbative techniques. And for that reason, it's major, well, to find like its leading effects, it's better to go to low energies where QCD is strongly coupled and to look for CP odd effects, which would be sourced by that parameter. And the basic example of such an effect is the neutral electric dipole moment, or EDM, which is nothing but the coefficient of that operator, so N being the neutron field and F being the field strength tensor of the photon. So that operator written like this violates CP and has the right, or it breaks the right symmetry to be generated by the theta angle. And you can, well, there are techniques to compute what the theta angle is going to contribute, or how it's going to contribute to this EDM. And for small theta angles, you get that prediction. On the other hand, the TDM has been looked for experimentally, and if you compare with the bound, which has that expression, you find that the theta angle has to be bounded and to be as small as 1 part in 10 to the 10. And so it's not just small, it's extremely small. And in the star model, as we said, we have no reason to expect that this is the case, in particular because we've already seen CP odd effects in the star model, which are nowhere near that small. Okay, so that's the strong CP problem. And like any well-defined and important problem in the star model, it has many solutions. So I'll talk about some of them briefly now and others in more details in what follows. So the question is, how do you make this theta angle appear to be extremely small at low energies, at least? And I would first like to stress that this question is really what I would call an effective field theorist nightmare, in the sense that it violates many expectations that you would have when you like to approach physics from the bottom up with an effective field theory mindset. So for instance, there are two things that are usually discussed in the context of effective field theories. One, which is that the heavier the physics, the less it contributes at the level of the dynamics of light, the low energy dynamics of light particles. And the second is that if you were to put by hand to zero a parameter at some scale, whereas there is no symmetry that protects that parameter, you expect RGEs, for instance, or just loop contribution in general, to regenerate that parameter. And interestingly, those two expectations are completely broken in the case of the theta angle. First of all, it receives contributions from all possible scales. It may not, depending on the model, but in general, all scales are susceptible to feed into the theta parameter. And also, it's barely regenerated at loop level. So for instance, in the star model, you could imagine fixing the theta angle to zero at some scale, and you may expect that the CKM matrix that breaks the same symmetries as the theta angle could regenerate it at loop level. But actually, it's a classic result of Ellis and Gaillard that in the star model, the RG of the theta angle only start at 7 loop with this kind of diagram. And you can have like finite correction at the threshold of the weak theory, which are like 3 loops at best. And none of those are like even comparable to the scale, to the current bars, to the current experimental bars. They're way below. So yeah, so it's an interesting problem that kind of goes against some of the expectations you have if you're an effective field theorist. And so for that reason, it's nice that we have IR solutions to that problem, namely solutions which do not rely on whatever happens on the UV, which are completely agnostic about the features of the UV theories. And I will classify them in 2 cases, those that make the theta angle unphysical and the ones that make it dynamical. In the first case, you would rely on the fact that if one of the defining quantities in the theta angle happen to be ill-defined, the whole thing better be unphysical. And one way of doing this is if those mass matrices have a 0 eigenvalue, in which case the determinant is 0 and the argument of this determinant is ill-defined, which would happen, for instance, if one of the quarks were massless. Another way of saying this is that if you had a massless quark, you can use its chiral rotation to absorb the theta angle, and it would not be regenerated in any other coefficient in the Lagrange. So that would have been a very nice solution to the strong CP problem, but at least in its most minimal form, it's been excluded by lattice study. In the second category, you may just wish to make that theta angle dynamical, namely you would like to interpret it in terms of the VEV of some dynamical scalar field. So that scalar field then bears the name of the QCD axiom, and it's at the core of the page-shipping solution to the strong CP problem. So then the question becomes, is there some dynamics that drive that axiom VEV to 0? And the key thing is that it happens to be the case, namely the QCD vacuum happens to have an energy minimized precisely when that VEV of the axiom is 0. Oh, sorry, yeah. So yeah, in that case, you have like the new spurion that complements the theta angle, which is the theta angle plus the dev of that action. And that relaxes to zero due to the dynamics of QCD, algos, for instance, are useful in the buffer with that here. A great aspect of the action, which motivates why it has been so much studied in the last year, is that it is also a great dark matter candidate. So the oscillation of that scalar field would behave like cold dark matter. It could make out for all the dark matter budget. Actually, there's a parallel that can be drawn between those two solutions, although I like separate them. And in that case, there's a way of understanding the whole story as being the fact that the eta prime wave plays the same role as the action, which I think is something you can make slightly more well-defined in large N versions of this. Okay, and yeah, you can navigate between these two pictures with using non-minimal model building. But that's all I'm going to say about these IR solutions. They're just very nice and very important. I may just say, just in passing, that they are not completely IR solutions in the sense that you have to understand some aspects of the UV theory to make these solutions work. For instance, in the case of the action, you have to be sure that nothing else contributes to its potential and nothing is susceptible to like shift its wave slightly away to zero. Because since we're dealing with effects as small as 10 to the minus 10, even like very suppressed contributions to the potential can kill your solution. So there are some UV aspects still to these solutions, but I guess it's still fair to call them IR solutions. In the rest of the talk, I'm not going to discuss these kind of solutions. I'm going to turn to other ones, which I would call UV solutions. Which, sorry, please. Yeah, so you can still do something of that sort using non-minimal model building. For instance, I can think of models of Franz and Hook, where you use the same idea. Like there is nowhere in your like, EFT. There's no EFT where you have a massless Goldstone, for instance, but you can still have some massless quark thing. So, for instance, the basic model I have in mind is like the two things that look like QCD related with the Z2 and some bifundamental fermion that has no mass. It plays the same role as in the quark in that case. So in the pure standard model, that doesn't work. I mean, if you add nothing else, I think we've measured quark masses to be non-zero now.
Just saying there's a common object which is massive.
Exactly. So this logic can be generalized in a way where nowhere in any EFT do you have a massless Goldstone. Yeah. So yeah, that's what I would put in the non-minimal model building. Okay, so instead today I'm gonna rephrase these things not as nightmare, but instead as a cure. I mean, those two features of the theta angle can be used to our advantage to solve the strong CP problem. Namely, we can we can engineer the contributions at all scales so that they cancel with the one of the quarks. And we can do this at any scale using the fact that the RGEs of the star model or something similar to the star model would not regenerate theta. So we are going to use those two features to build a model where theta is zero in the IR. And the way to make it, so you want to make it zero at some scale and you want to keep it zero at all scales. And the way to do it is to use symmetries. So as I was saying earlier, this GGDO operator breaks both P and CP. So if P and CP happen to be symmetries at some scale, then at that scale, the theta angle has to be zero. And then you want that, you want to rely on this to make it zero also in the IR. So that logic is at the core of P or CP solutions to the strong CP problem, and I'll focus mostly on parity. Of course, neither P nor CP are like genuine symmetries of the star model, so they have to be broken at some scales. So, and usually people use spontaneous breakaway. And so you're going to assume that P and CP is a symmetry somewhere in the UV that is spontaneously broken so that we don't see it in the star model.
So you want to assume that the C and CP be a gauge symmetry?
Well,
you have to do that. Because you want to start with CP and UV.
Yeah, that's right. You don't have to. I mean, depends what your bias is, I guess. But if they are just global symmetries in the UV, that works fine, right? If you're sensitive to arguments that say that global symmetries are not exact, they are always accidental or things like this, you could consider them to be gauged with the same effect. But I think just global P and CP at some scale is perfectly fine. Yeah. Like the Page-Quinn symmetry is global in the minimal model. Sorry, can you? That's right. Yeah, I'll come to that in a sec. Yeah. No, I'm just saying that imposing parity at some scale as a global symmetry, something you can do from the bottom up in the field theory. But as Tony is saying, right, gravity, we expect that gravity is going to spoil that at some point if parity is just a global symmetry. So
so that was my question. Is this consistent with gravity operating?
So yeah, you're gonna have a parity quality problem that you have to check. Yeah. So I'll get back to that. Yeah. You can introduce those effects. So indeed, you expect that in the most restricted, if you want to be conservative, you can still introduce some Planck suppressed effects and see what they induce. So that's something I'm going to discuss at some point. But yeah, you can treat this in the same way as you treat the Cauchy-Quinn quality problem. So these gravity contributions to the axion potential.
So it's at the same level. It's not as if this is better.
No, I don't think so. Well, we'll see. Like the scales are the scales are similar. Well, maybe we can compare this when I reach that point. So it's so much, yeah.
You're going to make sure you don't have to
Sorry, am I going to check that or?
Yeah, I mean, parity is consistent.
Yeah, that's right. No, indeed. No, I think it's not. No, yeah, I think. Say it again, sir?
If you are new millisecond potential, smaller in size. So that
Sorry, I'm not sure. No, I mean, I think it's correct that that imposing parity, you're gonna you have two options, right? 0 or pi. Yeah, this I agree, and I don't think I'm not addressing this anymore. I think this is always around.
But parity, of course, parity is massive broken.
Yeah. Yeah, that's what we rely on spontaneous breaking. I'll show you.
So
Yeah, it's going to be emergent. Yeah, well, at least it's going to be exact and then broken in a way that is consistent with the star. Yeah. So I'll be discussing mostly parity. But let me just very briefly say that there are the major part of most part of the literature on that topic deals with the so-called Nelson bar solutions to strong CP, in which case you're using CP as a symmetry in the UV. And you're generating CP breaking that you need, for instance, in the CK matrix by turning on some scalar wave that happens to be complex. So that has a phase you cannot redefine away. So very roughly, this defines the class of Nelson bar models. Instead, I'm going to rely on parity, which is still not a symmetry of the star model and needs to be spontaneously broken. So to see what you can do, you start from the reason why parity is not a symmetry of the star model in the first place, and it's not a symmetry of the star model because you have these quarks which are chiral, and we have left-handed carrying, leaving the doublet representation of SU2, and those right-handed fields which would have looked like the parity conjugate of these left-handed ones, which do not transform into SU2. So yeah, you have potentially two ways of solving this. Either introducing new fields which complement these ones into vector-like objects, or introducing new gauge groups which turn this into a doublet. In the first direction, what you're doing is interpreting these two right-handed quarks as rising from a doublet and hierarchy. So you're extending your gauge group that way. So instead of having SU2 U1, you add another SU2 factor. So now this SU2 factor acts on the right-handed quark, and that one acts on the left-handed quark on the star model. And at that stage, you're interpreting parity in a more general sense than the one that you find in textbook. So it acts on the fields as it does in textbooks, plus some Z2 exchange between those two gauges. So something which is, let's say, the 3-2-1, some hypercharge will descend to the 3-1-2. Yeah, so that would be a way of regenerating parity. Of course, we're not observing those additional gauge bosons, and we have to Higgs that group down to the U1 we're observing. And by Higgsing that gauge group, we are effectively spontaneously breaking parity. So that's one direction that people follow that define the so-called left-right models on which you can impose parity and therefore solve the strong CP problem. In the other, there's only one issue. Yeah, that's right. That's right. Yeah. So yeah, you have parity domain walls that are an issue, and I think it's been shown lately that they are like a bigger issue than regular domain walls, for instance. Depends again what your bias is towards parity. If it's parity is global symmetry, you can still always introduce some kind of bias. If it's a gauge symmetry, it's a much bigger problem that has been discussed, in which case you just don't want to have that breaking happening anywhere in cosmology at any time. So you want a reheating that happens lower. Yeah. But yeah, you have generically those domain walls that are expected.
How is your version parity?
Good. So yeah, so it's okay. I'll make it a bit. Okay, I have several of those versions in it. So let me. Yeah, in this precise case, it's acting on every field as in the textbook way. So like the parity version of this would be gamma 2, gamma 0 times this, right? And for the gauge field in the same way as in the textbook, except for the SU2 gauge field. So for the SU2 gauge field, the parity transform of W mu would be P mu nu W mu. That's fine. So I mean, well this one I think with this one. So you write the same textbook expression, but just you have a W1 that becomes a W2. So that makes sense. And we're going to do the same kind of tricks for the quarks in little y. So yeah, in another way, or probably the simplest way of doing this is that you compose regular parity with the simple change of the two. And that's what you impose in the field. Yeah, there's one issue about this theory, which is that as it stands, it cannot have any mass. Right? There's no way of combining these guys into mass term. So, and even with the new Higgs, that Higgs goes down to a U1, you can only write higher dimensional operators similar to the Newtonian masses to get the quark mass. So as it stands, that theory does not define a UV complete theory. You need some seesaw-like UV completion in addition. If you go to the other direction, I mean, you're trying just to add new fermions so that this guy belongs to a vector-like object. You're going to just reproduce those three and add right-handed indices, in which case parity would simply exchange those ones with those. Of course, this we know can't happen because those would be like new colored objects. And since it defines also a new Carroll theory, forget what it is. Yeah, you have to. Yeah, in general, those guys are too light. So I don't think that's right because of the math. Sorry, forget that.
So you would want to copy.
Yeah. So why am I not happy with this? Yeah. Okay. Sorry. I think that naturally the problem with this theory would be that the leading terms would be just the Dirac mass term between the two, and there's I think there's some kind of tuning problem why this Dirac mass term would not be the thing that. Yeah, it could be heavy, but in that case, you're not recovering the star model. Yeah, sorry. I should have made that chart. Yeah, so indeed, it depends how you couple them. So if you exactly, so what I wanted to say here is this thing, namely, if you just like give masses to these guys just to the Higgs mechanism here and here, so 2 copies of the Higgs mechanism, as you said, these things are completely ruled out. They cannot be made heavier because of unitarity of the Yukawa that couples them to the Higgs, and then they're completely ruled out in many ways, like Higgs coupling, Higgs production, Higgs decays, direct searches for these guys, etc. And so for that reason, people to build like consistent models, you have to do a mixture of the two. You have to add new quarks, and you have to add new gauge fields. That's what the bulk of the works about parity solutions to strong CP have done.
Is there any exemplary UV model which enjoys the higher gauge group, which gives you this exchange symmetry that's already symmetry that I believe? Is there any non-example? At least one UV model.
Yeah, so I think this left-right thing can arise in SO10, if I remember right. In SO10. Yeah. So that you can. Yeah, so if you impose SO10 times parity, I think there's a way of breaking that down to this. Yeah. I haven't studied that personally, but that's what I remember discussing with Lawrence. Yeah, but I think that exists. Yeah. So
exchange symmetry, which every
yeah, that's right. That's right. Yeah. Yeah, I think so. Yeah. Yeah. So I think you have. I'm not sure. I think you have to impose parity on those models from the beginning. So like parity is not emergent. But I think if you do that, there's one scale where it looks like this. But yeah, so in practice, you're doing both things. So you're adding new fields, and those fields, the new fields are not charged in the hour institute, but the starting institute, but the second institute. So the models in the literature mostly have like that kind of content, and the one I'm going to discuss also will have a similar field content. Okay, so yeah, those are basically the building blocks of all those at least of all the theories that we know of in the market that do this parity solution. And of course,
it also applies with space-time, right?
Yeah, that's right. Oh, yeah, good. So yeah, the transformation is indeed. So you send that guy to that guy and x minus x. Yeah.
Right.
But
that can be also arising from the breaking of this.
No, so I think that's why you have to add the parity by hand. Okay, I haven't studied that in full detail, but that's the statement I remember. That yeah, if you start from mesothelin times parity, you can land on that. Yeah, that's what I think happens. No, indeed, yeah. I don't think parity emerges. Could be, yeah. I don't know. Good. Right. So okay. So as we said, right, parity is only active at the high scale where all the groups are still like describing massless modes. When you go below the mass of the Higgs, well, below the wave of the Higgs that is using this sort of information, parity is not exact anymore, right? It's quantitative. Oh.
I can give
no, so
just have a
oh yeah, if you do the, yeah, so yeah, good. So those, yeah, you can do this with the bidoublet, that's right. And I think those problems have issue with the phases you're gonna get when you spontaneously break. So I think they have issues solving the strong CP problem because they are regenerating phases through the Higgs. Right. Sorry, yeah, you're right. Yeah. Yeah. No, but yeah, you're absolutely right. Sorry. No, I think I think those things are correct. Yeah, no, indeed. The Higgs sector I'm assuming here is a Higgs sector where you have two copies of the Higgs, which one that transforms in S21 and the other one otherwise. Indeed, yeah. With the bidoublet, you could give those guys a mass, but I think in the most naive non-supersymmetric version of that, you're not solving the strong CP problem. You're reintroducing phases upon spontaneous breaking, and that you don't want to do. You don't want to do it for the reason I was about to discuss, namely that you have fixed theta to 0 in the deep UV, but you also don't want theta non-zero being regenerated either through the spontaneous breaking of CP at the same scale, or through just the fact that the CPA matrix now can source the theta angle through RGE. So you need to check that doesn't happen. In the star model case, basically you want a model that behaves like the star model, so where all the loop corrections to theta will be suppressed because of the flavor structure of the theory and the small couplings, etc. But actually, that does not happen in all extensions. For instance, that paper showed that the minimal model that you could think of has a Dirac mass mixing. So for instance, if you go back to that slide, those two guys can mix. For instance. Yeah, those two guys can mix. So they have a Dirac mass matrices. They have a Dirac mass matrix that mixes them that has phases in it, and so these phases are still there even if you impose parity. So parity will remove some of those phases, but not all of them because you're not imposing CP. And for instance, this paper that I was referencing a second ago showed that there are loop corrections to the theta angle that comes from these masses. So the fact that you're imposing parity and looking somehow like the star model does not imply immediately that you're going to get the same kind of suppression to the loop corrections to theta. So you have to be careful about this and check a posteriori that your BSM scenario does not regenerate theta in a way that is stronger than the star model. And that what has been observed is that like being similar to the star model is easier in what is called a mirror model. So a mirror model, I'll make it a bit clearer in what follows, but historically, the example, the way people have dealt with this is that instead of doubling the SU2, they double the full electronic sector of the star model into SU2 times U1 squared for this. And in that case, what you've done with the SU2 quantum numbers, you're going to do the same to the hypercharged quantum numbers. So you'll have the star model version, which is the 32160. Sorry, this should be 0. And this one will be the 312016. So by doing this, you're forbidding, for instance, this Dirac mass term that I just mentioned. So these two guys, for instance, now can't mix anymore. But this one has like a -1/3 charge under that guy, or this guy has -1/3 charge under the other. So for instance, by doing this, you're not changing your solution to strong CP, but you're killing some of the terms that were recreating theta at loop level. So that idea of mirror model, I'm gonna keep using that idea of mirror model. So schematically, you want to do something like this, where you have standard model fields that interact, and you have another copy of them, which is exchanged with the standard model copy to parity. So here I should say one should not. So this, despite that looking like brains in extra dimension, has nothing to do with this. So I'm just using this to say that you have some fields which interact in a way similar to the standard model, some other fields that interact with themselves in a way similar to the standard model, and there may be some portals between the two. But those guys do the same for this spacetime. Yeah, they have their own. Yeah, exactly. So yeah, for instance, you can imagine a theory which is like exactly the standard model and exactly the standard model copied, right? And impose parity as being the symmetry that acts on X and X and exchanges all those fields. And Higgs has to go to Higgs prime. In which case, yeah, then the spontaneous breaking of parity is just the question whether those two Higgs are the same level. Yeah. And actually, I find it funny that model. Okay, it's mostly semantics, but that you could claim that if you're doing this and there's no mediator, that the standard model doesn't break parity. But okay, simply because you gave a broader meaning to parity. Good. Okay, so that's the mirror world idea. However, to solve the strong CP problem, you still want some amount of negation between those two worlds. Simply because, for instance, if you just like fully copy the standard model, so for instance, if you had gluons here and here, parity would simply imply that the two theta angles are anti-correlated, up to this pi ambiguity probability that we just discussed. But that would not be what you want to solve the strong CP problem. So what people have done is to consider that. So the model we've been discussing in the busy slide before is a model where there's a mirror world, but so everything is copied, so Higgs, the interactions, the forks, etc., except the gluons. So the gluons are shared, and they're the portal between those two worlds, which is doable, which is allowed because the gluon interaction like respects P on its own. So you don't have to. It's consistent to exchange those two worlds, except for gluons. And if you do this, then the theta angle is 0. So that's basically the premise of all those papers that I mentioned before. And then, of course, since you have like colored particles here, you want the two Higgs to have different waves simply because we haven't seen those new colored particles, and you're naturally driven to the phase where P is spontaneously blocked. Good. I don't know when. Okay. Yeah. Oh, yeah. Sorry. That's all I wanted. Yeah. So now I'll turn to what we've done. So all this was review so far. So what we've done is to take this mirror world idea and try to revive the idea that it would be a complete mirror world. So a mirror world where all the standard model is copied, because we were wondering like why would you treat the gluons differently in any way, differently than the other gauge fields. So in our study we noticed first that picture where the gluons are like a gauge field that is shared and that is mediating interaction between the two worlds, can arise in the IR from that picture. So a picture where you have really like two mirror worlds, including two versions of the gluons, as long as you have some bicolor mediator that takes a wave, so that in the deep IR, those two gauge groups, those two color gauge groups break to their diagonal subgroup that would look like the gluons we see today.
So on the important of the lines
So that's up to you. So to solve the strong CP problem, you could embrace both options. So I'm gonna work in the case where it's massless. Yeah. So there's no Higgsing of these two ones. Yeah, I'll discuss that. You could. Yeah. So for the strong CP problem, it's irrelevant that you have kinetic mixing, but for cosmology, it would be very important. Yeah. Please, yeah.
How many use cases?
So there's a second Higgs that is needed, and that can be scalar or something else. So I'll discuss cases where you have scalars and cases where you don't. But yeah, the new scalar I need is the Higgs, the second Higgs. This one I need. Sorry, what?
With our Higgs, we already have a layer.
Yeah.
Now
Good.
we get a second layer.
Yeah. So
our hierarchy probably the this candidate itself and probably not. But for this one.
yeah. So yeah, what has been shown, I think, is that so if you write the most generic potential for the two Higgses and you like minimize it, including some self-breaking of parity or something, you're not doing worse in terms of tuning than in our Higgs case. I think that has been shown. Like the tuning in this 2 Higgs model is the same as in the single Higgs model. If you just think of the quadratic divergence. Okay. So no, I think it's because like it's a 2-step question, right? So you have the Planck mass, and then you have the Higgs, the scale of the second Higgs. Then much below you have the scale of our Higgs. And I think in those models. That's right, exactly. And so to separate them in that way, you have to tune 2 things: the thing that brings the Planck mass down to the scale where you have the second Higgs, and the thing that brings the second Higgs down to the scale where you have our Higgs. And I think the tuning in total is a multiplication of the 2 that amounts to the same tuning as that you would need to bring the Planck mass down to the TeV immediately. I think that's what has been shown in those early papers on the subject. Yeah, we can discuss more, but yeah, this question has been asked, and I think I think the claim is that you're not making it better, but you're not making it worse either.
In the motivation, your question, there was a factor of 10 to the minus 10.
Yeah, that's right.
You have to introduce some other things in the tuning.
Yeah,
You
so
have to say how badly you tuned it.
yeah, good. So I think the claim is that you're not tuning it. Okay, the difference with it depends how, like, which kind of tunings you like and you don't like. So if you don't like, if you think the tuning of the hierarchy problem in the Higgs sector is better than tuning a small parameter in the Lagrangian, then we are making it worse. If you put them at the same footing, you're not making it worse in those kind of problems. I think that's the case. Yeah. So you're gonna have to tune something in the Higgs potential. That's right. But if you measure the tuning, it's equivalent to the tuning of the Higgs that we already have. I think that's what is usually claimed. Yeah, I can discuss this more maybe, but I don't have any slide on this. But good. Yeah, that's a funny aspect. No, but no, that's not the tuning. Well, the tuning is different actually. It's a funny thing because the potential so if you write the potential of the 2 Higgses with order 1 coefficients, depending on the order 1 coefficients, the vacuum is different. So you have one vacuum where the 2 waves are equal, and one vacuum where one has all the wave and the other one has 0. So that's a natural vacuum. The one where one of the Higgs sucks up all the wave and the other one has none is like a natural vacuum. So that's one out of 2 options. Like half of the parameter space gives you equal waves, and half of the parameter space gives you one Higgs with all the wave and the other ones with 0. So the tuning problem in that case does not become like take 2 waves and make one small. The problem becomes take a 0 wave and make it slightly positive.
That's because I think there's a quartic interaction.
That's right. Yeah,
This is the Higgs
yeah.
prime.
Yeah, that's right. You have a mix. You have a cross quartic. Exactly. Yeah. So yeah, if you don't have that cross quartic, yeah, they have to be. Yeah, that's right. Yeah, no, indeed, that's because of that. And that's cross quartic. But yeah, having one very small is natural. What's hard is to lift it to something a bit not 0, a bit not 0. Okay, I'll come to that a bit later, but that's right. Yeah. So yeah, we'll have those issues definitely. Yeah. Yeah, absolutely. Yeah. Yeah. No, indeed. In this model, you don't want to reheat a 10 to the 16 GeV or something. Yeah. Otherwise, you're going to produce all these guys, and some of them are stable. You're overproducing things which are colored. Yeah, it's a complete mess. Yeah. So yeah, the cosmology of these things has to be modified. I'll give you an example of how, but it's yeah. Good. Yeah. So here we were happy to see that there is at least one UV completion that looks like a complete mirror world where all gauge fields are like treated equal. And I think so that for the strong CP problem is not very interesting because the strong CP problem is already solved at that scale. So having like another UV completion of this is not really interesting for the strong CP. What's interesting is that because of the fact that the theta angle does not run much, you could start from the same place, namely like the two mirror worlds exchanged by parity and some bipolar mediator that's going to get a wave at some point. And you first break parity. So the largest scale is the scale of the field. That's then you're landing at intermediate scales in that kind of description, where you have the standard model with some theta angle. On the other world, you have what looks like the low energy effective field theory. In our world, that just lifted up. So you get gluons, photons, a few quarks, electrons. But because of parity being exactly the UV and because of the theta angle running very weakly in those theories, you get a theta angle that is still anti-correlated with the one in the star model. So that kind of, and this you can go on with breaking the bipolar deviator. And that's the kind of hierarchy of scales that we're going to consider that gives us new pheno with respect to what has been looked at in this context. And that chain of breaking gives you a new perspective on this effective field theory nightmare that I was mentioning before. So imagine you're probing higher scales at some point and you see these new gluons arising. So they're just new heavy gluons that you just found at colliders. But if you happen to probe their theta angle, you'll find that they're having anti-correlated with the theta angle. Their theta angle is non-zero, order 1, but anti-correlated with the theta angle of the standard model. So that looks like also an incredibly surprising tuning. But it's probably even more surprising the star model because those things look very much different. They have an order 1 theta angle, but they're just exactly anti-correlated. Okay, so I'm going to focus mostly on this hierarchy of scales. So the scales where the parity breaking happens to be the largest, and it's followed at lower energies by the breaking of colors, the two-color group by this bipolar deviator.
Wait, this is me that these energy scales out.
That's right. Yeah, that's right. Yeah. Yeah, in this model, we have a non-zero theta angle as long as you have two gauge groups. Yeah. That I was going to show it a bit later, but indeed, it's only in the IR that you can see. Yeah, I'll show you how in like a few slides. Yeah, so the starting point is this, and the field content is this ugly thing. So basically, you have the standard gauge group that you copy, you have the standard model force that you copy, and like that block is sent to that block in the parity. So parity acts on the field as in the textbook, and you just add primes on the expressions you extract from the textbook. That's how parity acts. And that action of parity, so in here and here, you have a theta angle, you have Yukawa matrices, you have gauge couplings, etc. And parity enforces that the theta angles are anti-correlated, that the mesh matrices are Hermitian in any flavor basis. And these together impose, like, from this, you can derive that the physical theta angles in the two worlds are also anti-correlated like this. Then you're going to break the two-color group using this bicolor mediator, which can be anything. Well, as long as it's bicolor, I'll give you some. As long as it lives in the three of that group and the three of that group, I'll give you examples of how you can do that.
After exchange, do you also impose, for instance, like complex? Do you need to also work with complex conjugating things to complete your zeta symmetry? Why Q should be like Q there?
Oh, yeah, that's right. Yeah, it's because
your exchange symmetries, you go for Z2, and then after that you use complex conjugate 2, right?
Right.
So that's your Z2.
Yeah. So good. Okay, that's something I didn't want to discuss, but yeah. So there's only one way of sending that data to that guy, depending on whether this is L or right, and that you call parity.
I'm just asking, like, what symmetry you're assuming. Then I guess I got it.
Good. So let's see. So yeah, given those charges, I'm sending that guy to the star of that guy. Yeah, that's right.
You're sending Q to Q prime bar.
Yeah, but yeah, these guys here are all left-handed in this language. Yeah. Yeah, there's something a bit funny about these models is that since you're composing parity with a Z2, you could as well like put C, the charge conjugation, in the Z2 and call it CP times Z2. That's absolutely equivalent. So there's like one way of it. So these guys you can compose. You can like redefine Q. Your building block can be either Q or QC, just Q prime or Q prime C, right? It's up to you to choose. And what you should impose depends on that choice. But there's like one unique choice. So for this table, I think I picked those guys left-handed, in which case this thing looks like a CP action, but not P action. But it's unique. Yeah, you're right. Yeah, that's why that. But in any case, that doesn't depend on that choice. There's given those charges and the parity of that guy, there's only one choice, and you use this. But you're right. Yeah. So once you introduce this bifundamental order parameter, you're gonna, if it happens to get a wave which is diagonal, which is natural, as I show you in a few slides, when you project along the massless QCD gauge fields, you find that the GG dual of that world and the GG dual operator of that world are equal. And that combined with this equality at the extreme right gives you that the theta angle in the deep IR is 0. So as you were asking, these guys are order 1 in the UV, and as soon as you break those two gauge groups to the diagonal subgroup, you'll find that the IR theta angle is 0.
at medium level.
At
The G bar is zero and
you mean up to loop corrections or what? Oh yeah, absolutely. Yeah, absolutely. Yeah, no, indeed. Yeah, this.
it's often break one expression you have that.
That's right. Absolutely. Yeah, this will become an approximate sign as soon as I put in the loop corrections. Absolutely. Yeah. But yeah, that's right. Yeah, another aspect of this relation is that the spectrum in this box is absolutely correlated with the spectrum of that box. So for instance, the mass hierarchies of quarks are exactly the same. And you can, for all quarks, you can write this kind of equalities where the ratio of masses of, let's say, the up quark here and the up prime quark here, the ratio of masses have to follow this relation. So our electroweak wave divided by the scale of parity breaking. So for that reason, you cannot, that scale of parity breaking has to be high. So you haven't seen the up prime quark, so it means that this guy has to be heavy, but we know that the top prime is like 10 to the 6 heavier. So all these consider like the collider bound on that guy that I'll refer to as V prime, coming from the fact that we haven't seen any of these new colored guys, imposes that this parity breaking has to live at high scale, like 10 to the 9 G. So it's very high scale parity breaking. Yeah, absolutely. Right. Yeah. There's no other confinement than the QCD confinement. Yeah, I'll come back to that also at some point. Good. So yeah, so this thing, as I was saying, you can get this large hierarchy of Higgs based either through self-breaking or radiative correction. So these things have been studied in those papers, for instance, where this claim about natureness was also made. Good. But okay, altogether, so that model looks like very heavy, right? Content, etc. But I would like to stress that it's very predictive. Like because of the parity structure, all of the phenos is captured basically by two scales. You have the scale where parity is broken, where this Higgs gets a wave, and you have the scale where this bicolor mediator gets a wave. And those two scales really capture all of the pheno. So later I'll show you like plots like bounds on the model in two-dimensional planes, and that will be like the whole space of bounds, not a projection. So I think that's, despite, I mean, you may or may not like model building, right? And maybe something in 10 to the 9 GeV, something you don't like to think about, but I find that aspect of the model exciting. And that's what makes me want to study it further, is that you get, for instance, later on I'll discuss the cosmology, and the cosmology is super constrained because of that. You don't have much to play with. You can only play with these two scales. And either it works or it doesn't work. And you don't have much to tune. And so the pheno is very different depending on the ratio of these two scales. So as I was telling, when this guy is the largest, you land on an effective description which looks like models that have been considered in the literature before. And the new stuff comes from when this guy is much below this guy. And for instance, if it's really much below, the first states that you may find in colliders are the colored bosons. So the ones that come from the heavy gluons that are Higgs, or whatever is generated by what you call this bicolor mediator. So yeah, this part of our interface would be the new pheno part, I guess. So on that respect, let me say just a bit about this bicolor mediator, and we consider two cases. Yeah. Right. Yeah, they're actually interesting. It depends. I think they're heavier than this because so it depends how you give them a mass. But if you give them a mass through the Majorana, through the Weinberg operator, so all the fermions, so this relation here works for all fermions but neutrinos in that case. For neutrinos, if you give them a mass through the Weinberg operator, this is squared. So like the push you give to an up quark, you give that push squared to neutrinos. So in most of the parameter space, the neutrinos in the mirror sector are heavier than the quarks and leptons, and they decay to those states. So yeah, if you give them a Dirac mass, then that scaling is reintroduced and they become the lightest fermions. But if you do it through the Weinberg operator, they are generally heavier. And I think in the case we looked at, they are in the tens of TeVs or something, at least. Yeah. And they presumably decay unless you tune something.
Would that actually impact like you probably can show it, but is that the strongest constraint on your sort of cosmology?
No, the strongest constraint depends what you want to do with the strongest. Well, there are many constraints. You don't want the domain walls of that guy. Well, you don't have the parity domain walls, and you also don't want to produce this guy. So this guy would be the biggest worry for us. So because of this ratio, you also know that the mirror up quark and the mirror electrons are close in mass. And we're going to try to make the mirror electron dark matter, in which case we have, we really don't want that other guy to be produced because it's colored, right? So it's a colored stable thing that's going to bind and form like fractionally charged matter. You really don't want that guy. So this, in the kind of story we're going to tell, this one is going to get worried. If you don't want anything to be dark matter, for instance, to reheat below, like much below all the masses of these guys, you don't have, if you reheat much below, there's no, there's no constraint. You're not going to reheat anything. Like the neutrinos will be reheated to either these heavy W exchange, which is extremely heavy, and
No, but the neutrinos.
well, I'll come to that. Yeah, but they don't have our electric charge, these guys. So if you do like U prime UU, for instance, it's charged, or even U prime U bar with charge. Yeah. No, absolutely. Yeah. If you that's that.
The neutrinos you get to
You're right. So yeah, the kinetic mixing will have to. Okay, let me come back to that in a few. Maybe sorry. We'll have more words to read maybe. Yeah, let me say very briefly about this bicolored mediator. So you can do it either through a scalar and or strongly interacting fermions. We looked at both. So in the scalar case, you just introduce a scalar in the 3 prime, which would be either 3 or 3 bar of the second group. You write its most generic potential that has the following form, and you're going to find that in a large fraction of parameter space, or the 1 fraction, I mean, the true vacuum of that theory happens to break 2 group down to the diagonal, which is exactly what I want. Or in other words, the valve that minimizes that potential is the identity times something. Okay, so in that case, you would recreate an extra hierarchy problem, as you were discussing, that has nothing to do with the Higgs one this time. So that's why and the good thing about this breaking is that because of these charges, it's not gonna couple to quarks in any way. So even if there's a phase that shows up in your valve, you can reabsorb it and it does not reappear anywhere. So it does not break spontaneously P and CP. We don't want like an extra source of P and CP breaking in that model, and that guy does not provide any. Sorry. Okay, and now let me go back to what I was saying. So we looked at the strongly interacting fermions just to have a natural model of this valve, so something that does not require adding by hand a new fundamental scalar. So we looked at the breaking of these 2 groups down to the diagonal in a technical fashion, where you use additional confining gauge groups and the fermion condensate that are formed to break those weakly coupled gauge groups. So there are several ways of doing this. So here's one way, or you add these new particles and new confining gauge groups of that sort. And if those confine before, those confining will give you the state of this diagonal breaking. So you're going to form condensate in these 2 guys, and you're going to form condensate in these 2 guys. That because of the SO3 assignment, that condensate happens to be a difundamental that we wanted, and that condensate also happens to be a difundamental. So those condensates forming, you're going to Higgs the 2 SU3 down to the diagonal SU3 in the way we want. So it's slightly heavier than the scalar, but it has at least no nature-ness issue. And so you have very I think we find like 3 or 4 different ways of doing this that are qualitatively different. So here, for instance, let me discuss 2. So depending on what you call this 3 prime, so this 3 prime could be either 3 or the 3 bar. You should impose parity either to extend these 2 lines or to extend these 2 lines. And depending on that choice, you either find that the 2 confining scale has to be the same or can be very different. So you get different pheno in those cases. So you have qualitatively different ways of doing that, but for the strong CP problem, they're all equivalent in the way that they do the same as that guy. Good. Let me just say a brief word about this. So as we discussed, I'm breaking parity. So parity is not enforcing in the UV that the theta angles are before.
So this is global symmetry break, strong dynamics that we Goldstone.
Absolutely, yeah. So you get a bunch of colored Goldstones, for instance, that get a mass.
Low energy, but they could be pseudo scale.
That's right. So so what we checked is that in these models we're not solving the strong CP twice.
Yeah.
This we check. So there's no axion. There is no Goldstone that is not either anomalous or eaten and that has a QCD anomaly. So some of them have a QCD anomaly, but are the eta prime of some of these guys.
But once you have like the massless Goldstones,
no, this would but we don't get any, it depends on the choices. I forgot which one. There's one choice that gives you Goldstone, one choice that doesn't. I forgot. You could get massless Goldstones, but those have no anomalies with QCD in these models. This we checked.
What's the topology?
Yeah, that's right. Yeah, but now I don't remember which one. Yeah, I think there's only one instance of all these models that we built of that sort that has a master Goldstone. In the other cases, they were either lifted by higher dimensional operators we could write, or by anomalies, or by or they're fixed. Maybe they're eaten by some gauge field. So I don't remember which one, but we have one. Yeah, good. So in these models, basically the same happen. I mean, the model is really like twice the star model. So in terms of these corrections to the theta angle. So the only mediators we have that could like generate new diagrams beyond the one we have in the star model are either the gluons, the bipolar mediators, or the heavy Higgs. And none of these couple in a way that has a new extra CP phase in it. So the only CP phase we have in the model that could drive a renormalization of theta is the CKM phase. So we have the CKM phase in one world and the same CKM phase in the other world. And we need a diagram that is sensitive to this object if we want to get the corrections to theta. So for instance, we have no bare mass that has a phase or nothing like this. So in practice, the diagrams we have are exactly like the star model at lowest orders, and then they even cancel in some cases. So what we can claim, we haven't checked much, but I mean, we haven't computed this thing, but what we know is that for just recycling the standard model argument, we need at least 3 loops to write something that may not be vanishing. And it may even be that the 3-loop thing vanishes. This we haven't checked. But in any case, it's a very small contribution. The one thing that is new with respect to the star model is that, as you noticed, we have this non-zero theta angle in the UV that gives you a 0 theta angle in the IR. And this non-zero theta angle in the UV is a new source of CP violation that manifests itself through strong dynamics. And in particular, we have to check the effect of the small instantons. So we have these 2 SU3 gauge group that break to 1, and you can have constrained instantons down to the scale where they break. And you have to check that the summing over those instantons are not gonna generate corrections to the theta angle just by closing some fermion loops and so on in the top vertex. So this we checked, and it happens that for our parameter space, that does not happen. Namely, all these small instantons give you corrections which are suppressed enough not to be competitive with the 10 to the minus 10 bound that we have in theta. What's interesting though is that in some parts of the parameter space, these small instantons can give you the largest contribution. So despite the loops looking very much like the star model, we can have a model where the theta angle is like 1 or 2 orders of magnitude below the bound that is currently set. So it may be that we find in this model at some point through new experiments, we find a theta angle that is in the ballpark of 10 to the minus 12, for instance, that would be generated by small instantons. Good. Okay. That's right. Yeah. Yeah. Except that for us, it was and it could have been bad. Yes. Those are the same instantons. Yeah. Good. So yeah, the bounds on the model, as I was telling you, can be summarized in like a 2D plane, and they're like, it's not a projection. That's all of it. So we've included some bounds. So here I was discussing this quality problem. So for instance, you can write some operators in the UV that you can, for instance, take to be Planck compressed. So that guy, for instance, is an operator that respects parity, but upon spontaneous breaking of parity, will generate the shift in the 2 theta angles. So the theta angle shift in that group and the prime group will be the same after spontaneous parity breaking. And for that to still be compatible with the bound we have on theta, you cannot send the Higgs wave too high. You basically have a bound of the ratio, the Higgs wave, the Planck mass that is shown here. Another bound comes from the running of the second gauge group. So basically, we want to Higgs them to the diagonal. But if one of them happens to confine too early, then it will completely change the potential of our scalar of our confining fermions in a way that would completely destroy our solution. So we have to be sure that the second SU3 does not confine before we Higgs it. That puts this big red region, that rules out this big red region. And the reason why we can rule it out is that parity is so strong that if you give me, the constraint on parity is so strong that if you give me the scale of parity breaking, which I think is 10 to the 9, that's what, and you give me the scale of curve breaking, which for the solid line is the 5, I can compute the full RGs of the star model gauge coupling, the masses. So in that case, when the RGs look like this, so I know how to derived up to the new states, then I know one condition that means that encodes the fact that these 2 gauge couplings will match into QCD, but I have another condition, which is that they should meet at the scale where parity is that. And these conditions are sufficient for me to determine the forwarding. But at some point, I know that the second QC coupling, the second color coupling will go up. And that's what I don't want to happen. And finally, we have like LHC search is bound. So we have new color particles, which are these mirror quarks, which exclude these regions where for low parity breaking state, where they would be too light. And you have also searches for the heavy gluons that are predicted because we Higgs the two gauge groups down to 1. So that gives you this extra bound. So roughly, it's a model where the parity, where the color breaking has to be at least a few TeVs, and the parity breaking has to be 10 to the 8th GeV. Yeah. A mixture, so I don't know how to calculate, but I don't know today how to calculate. I suspect that people know how to calculate this, but I strongly suspect that I think it's fair to say that the potential has to change, right? So, like a VEV, it's so for instance, if you take the scalar, like the VEV of the scalar is turning on. I think you can like break it in many ways by like nucleating stuff and so on. So I think the expectation is that its potential is gonna stabilize it to a place where this SU3 prime is not broken. If SU3 prime confines before that Higgs is supposed to pick up a VEV. I haven't done the computation, but I don't see how that could still work. But yeah, you're right. I don't know how to prove it. I'm sure someone knows. Yeah, and you have some model-dependent bound on the scalars that haven't made explicit because they really depend on which choice you make. In this case of the scalar mediator, that depends on how you choose the different parameters in the Lagrangian. But roughly speaking, they would look like this. They have nothing to do with the breaking of parity. They just have to do something with the color. Yeah, I wanted to say something about dark matter, but am I over time or should I stop? Or maybe I can wrap up in maybe if you give me 5 minutes or so. 5-10 minutes should be enough. Okay, good. Okay, so all this story was the work we published already with Lawrence and others, and I wanted just to say a few words about the cosmology of this model, in particular about the possible dark matter candidates that we have, and this corresponds to the work in progress that we're about to publish. Good. So in these models, we have like this whole tower of new particles, and because of the structure of the model, we have a mirror baryon number, a mirror lepton number. So we have many new stable particles, but several new stable particles, and some of them are therefore dark matter candidates. So we asked the question: is it possible that one of them is dark matter in at least some cosmological history? And by checking the different particles, checking which ones are stable, which ones are neutral, you find that there's only one candidate, which is the mirror electron. So all the other mirror particles either have colors, or decay. None of them has like both no color and stable and stability. Good. So your target is the mirror electron in that mode. The problem is that, as I was discussing, you cannot really decouple it from the mirror up quark. Because of parity, their masses are correlated, and they are like super strong bound on the rate density of this kind of object. So the mirror up quark is the lightest object that has the mirror baryon number, so it cannot decay. So it will stay there as a subcomponent of dark matter, and that subcomponent of dark matter is extremely well constrained. So these guys are going to hadronize. They can form like bound states between them, but there will be a rate density of bound states where they hadronize with our quark. So you can, for instance, with the mirror up quark, you can form, as we discussed, U prime U bar or U prime UU, things like this. And these guys there are like many experiments looking for them. So for instance, you can recast. So these papers, for instance, these papers have looked at this question. So whether it's possible to have, for instance, these stable fractionally charged particles that would be U prime UU, for instance. And you can recast, for instance, monopole searches or searches for things that ionize matter in meteorites. I mean, there are several different bounds of this, which there are many uncertainties on those bounds and on the dynamics, but I think what we extracted is a rough range of that sort. That the yield of the U prime quark has to be at most 10 to the minus 9, that's dark matter. And in our model, that's a very strong bound, simply because, as we said, the masses are fixed by parity. So for instance, in that case, where I chose the parity breaking state between the 9 GeV, and we again have these two scales for the color breaking, you can really compute the RGs of the ratio of U prime over ND prime. And you see that, for instance, the dark matter candidate is only a factor of 2, at most lighter than the form. So that like restricts a lot the cosmology you can think of in this condition. For instance, you cannot do freeze out with or without dilution. if you freeze out E prime, you're gonna freeze out a large fraction of U prime anyway. So it's really, yeah. So this you can't really do. In the previous papers, what was discussed is either non-thermal mechanisms, like for instance, the inflaton decay to just E prime and nothing else. People have considered other dark matter candidates, like the mirror neutrinos we mentioned. If some of the mixing that are allowed by parity are tuned to very small values, you could have like long-lived neutrinos and so on, which could be dark matter candidates. People have also considered like adding ad hoc fields, so an extended spectrum to have fields that play the role of dark matter. But here we really wanted to check whether there's at least even weird cosmology where one of our fields is dark matter in a thermal way and works. And the only thing we could find that works is the sequential freezing mechanism from the mirror photon. So what we are doing is we start from a standard model bath of only the star models, no mirror particles, for instance, so that's our starting point. And you can freeze in the dark photon, and that dark photon you can freeze in again the dark electron. So we found that the parameter space that works has neither that guy in equilibrium with the star model, neither of those two guys in equilibrium. So it's really a succession of two freezing. Yeah, you're right. We also have this. Yeah, we are adding this. Sorry, I just put one. You're right. This one is also. Yeah, we have that in the Boltzmann code. Yeah, it's included. But you're right. It's larger. Yeah, that's how we do it. I just want to stress that again, it's really like there's nothing we can tune. So it was either yes or no. Namely, here you see that there are only gauge couplings which are fully fixed to the ones we know because of parity. There's a loop of U prime, which is the lowest, like the negator of lowest possible mass that can do this, and this mass is fixed by parity and the upward mass, and the same in that point. So there's no free parameter. We can only check, well, except the U. So there's only the scale of parity breaking that will tell us the mass of U. That's all, of U prime. No, it's not really. It's very ugly, as you can see, because as you will see in a second, it's ugly because we require very specific conditions of inflation for that to happen.
So you're saying that down the prime you don't have the
That's right. Yeah. So in the case we're looking at, it's strictly speaking, it doesn't have enough energy to produce this guy. So it's really on the Boltzmann tail. So U prime is also produced on the Boltzmann tail, but because now the ratio of 2 that we have between the two masses becomes an exponential squared, and that thing can be low enough. So we check that it's low enough, but both are produced. Yeah. Just the U prime is produced with a lower Boltzmann suppression. It's extremely constrained. Yeah. No, I mean, I'm not claiming in any way that this is a miracle. I'm just saying that we found at least one parameter. Like we find one scenario where the production of dark matter is thermal, which was our goal. But I don't ask you that you're buying that tomorrow later. But and in particular, we have inflation. We need inflation to behave in a specific way. So we need especially reheating. So we need reheating to the star model only. So that's okay because of the breaking of parity. So for instance, if reheating happens through a Higgs portal, it very naturally goes our vector rather than the Euro because of the huge Higgs difference, the huge Higgs mass difference. But we think that we also need that the maximal temperature reached during reheating is comparable to the final reheating. That is the biggest constraint on the kind of inflation. Simply because it's hard to explain non-numerically, but basically if we have a large hierarchy of these two, our freezing of E prime will be diluted, so we need to slightly overproduce E prime, and that will also overproduce U prime in the way that. So we kind of need, and of course we need something I didn't say, but we need the reheating temperature to be much below the scale of this guy. So yeah, it's quite constrained, but it works. If you mind.
The point of mirror.
Oh, good.
The earlier question you said depending on how they get their mass, they can actually be the light.
That's right. Yeah. So you can either make them the light state, but at least you can make them long-lived. That I think is doable. So I think the main decay of these guys would be to Higgs and electrons. If you tune nothing, the major decay is to Higgs and electrons, I think.
But if you give them direct mass, that they don't.
Oh yeah, good. So if you're doing this, they can be dark matter. Right. It's just that so I think people have looked at this case. So you can have them dark matter, but then you need to produce them at very high scale, at the parity breaking scale, right? I think they decouple from the bath as soon as the mirror with interactions are not efficient anymore. So that's when that decouples. And you're going to produce the rest of everything. So I think how people dealt with those issues is to use another neutrinos that would decay and dilute the rest. Sorry, I forgot. We haven't looked at it, but yeah, this case have been looked at. So I know that there are papers who made sterile neutrino dark matter out of this that have to rely on other neutrinos decaying to dilute stuff. But yeah, sorry, I can't. Yeah, I'm not sure I'm making sense in all details, but yeah.
This issue of the maximum mass, I mean, that it's close to TV heating is not necessarily a problem, but that it's low is a problem.
Yeah.
The TV heating you can make low, but Tmax you cannot make low.
Yeah. Okay.
It's always going to be actually quite large, so long as because unless you give up the density fluctuations from inflation, because that's set, that scale, the inflation scale,
right,
is set from that.
Yeah.
And then there's always gravity. Gravity is always going to get you a maximum, a T max that you can't go below. It'll have nothing to do with the heating. That will then to get that, but you will start making particles at very high energy, no matter what you do. That's coming from inflation.
So you're saying there is no.
You can't make T max is not something you can make arbitrarily small.
In any model of reheating, I think we at some point we were looking at these reheating models where
Reheating is different, right? Because reheating,
Very likely.
Yeah.
That's the
they need very little
Not
energy.
small,
And it's not the mass. It's the energy density in the. You can have a mass that's infinite, right? Because that's just the shape of the potential around the net.
how much energy.
How much energy?
Per individual event.
Yeah. And that is set from the density fluctuation. Sure. That's the normalization of the full spectrum.
Yeah. Okay. Good. You should tell me more about that. Yeah.
It's
okay.
just that energy initially will produce some thermal back. It'll be a sub-dominant, so maybe it's still okay for what you're trying to do. I don't know. That itself is the problem. The what T max is telling you is that there's some thermal bath, which is not dominant. It's not. It's a small component to the total energy density, but it has very high temperature.
Yeah.
Right.
Okay. No, because
reheating means that you get that bath eventually. The energy density in that thermal bath starts to dominate over the inflation.
Yeah. Right.
What's wrong if I go to? I understand that it's what's wrong if I go to like very small mass parameter and very huge overflying the flare. Like if I
but it's all coming from. It's all happening right after inflation. It's not late, right? You're thinking about something happening late, like the decay is happening late.
Yeah.
This is not coming from the late decay. This is coming from production very early on, right? Coming out of inflation, so it really carries the energy density of during inflation. Well, then that's then hard to do.
Yeah.
Yeah, if you have a low Hubble scale, but that scale, well, it's not the flatness of the potential. The flatness of the potential is always flat for inflation. It's not the flatness. It's the amount of energy.
No, but the inflation fluctuations have 1 or 5 dollars. Yeah, so I will what they're saying. We go to some.
Yeah, so if you make an unusual,
from
model where the Hubble scale during inflation is very low.
Yeah.
so extremely super slow roll. Yeah, let's say.
Yeah. No. Okay. We had this kind of things in mind. I mean, yeah, our standard is quite low here, right? So we're looking for one inflation parameter point that works. So indeed, we allowed ourselves to think about any crazy potential and any Hubble scale that would match
It detracts.
Sorry?
It detracts a little bit.
Oh yeah, sure. Yeah, no, we agree with this.
At some point, the cure is worse than the disease.
That's right.
But getting back to the thing that you actually want here, so actually requiring or wanting Tmax to be about purity. So you're worried about producing this whole spectrum of stuff, right? That's heavier.
Not necessarily the whole spectrum. I think our problem with Tmax much larger than purity is that so we're freezing in the E prime, right? So we're gonna have to freeze it at Tmax. And
yeah,
then it's gonna be
some amount of dilution. Right?
good, but so for that to hit the dark matter density today, you need to overproduce it at Tmax with respect to something with a dilution. And if you look at what that means in terms of like how large the exponential tail, like how far in the Boltzmann tail you have to be, I think we showed that it implies that the exponential tail when you would produce U prime is too large. So I think so the dilution you have to account for to get the right amount of U prime means that you have some kind of strong freezing. That strong freezing has an impact on U prime. Yeah, that's why we didn't want that to happen.
Okay.
I mean, yeah, we can afford like a few factors about the one, but not 10
So
to 5.
it's just because the U primes and U primes.
That's right. Yeah. No, of course. Yeah, if we had a way of making the U prime like vastly heavier, then there would be no issue. So yeah, we would just freeze in at Tmax and then. Yeah, no, that's all because of this. All because of these guys that we don't want. Absolutely. Yeah. Good. Okay, let me wrap up maybe. Yeah, good. So okay, that's the plot for the dark matter thing. But yeah, I just wanted to highlight that we also have a plot with this, just the 2D plot of this, where this colorful region would just be the ones where we make dark matter, and maybe in the direction of having something. So here we don't have any reheating temperature that would work, even with this and reheating. And here we could. So these two regions account for the fact that we know NU to lattice studies, for instance, up to an error that can be at least as large as 20%. And since we're doing freezing, this 20% can be like very important. But so if our U core is 20% heavier, then U prime is something similar to that heavier, and therefore it's easier not to produce it. But for instance, these regions like populate now this part. Yeah, there's one thing that we also have to explain is this kinetic mixing that someone asked about an hour ago. So the kinetic mixing is going to induce some direct detection bounds of the model that are this grayish, and this grayish region is what's included. So here we're making also a very strong assumption, which is that there is no kinetic mixing in the deep UV. So which you could do, for instance, if you imagine that the U1s, for instance, are embedded into a larger group, that can give you like a UV boundary condition where the kinetic mixing is 0. If you do that, there is still like some well, let me skip this, but yeah, even if you impose that, there's this ugly for loop diagram that generates a kinetic mixing, and despite being for loops, it still drives a detectable signal for indirect detection. And the main interest of our model, so if you compare with the models where V3, so this scale of color breaking is definitely high, it's irrelevant for the study of speed, all of it is excluded by dark matter directly from this for loop thing. When you sit here, when the color breaking is happening at low scales, this for loop diagram is going to be shut off for most of the RGB, simply because that gluon cannot go to Q prime and Q, you have to go to the loop of the mediator. So above that scale, this doesn't happen. And you have a further suppression, which comes from the fact that if U prime is heavy, you first have to integrate it out, then you have some kind of a U prime some power suppress temperature that you can kick in as soon as you can. Anyway, all these things put together open up a region in parameter space that, however, requires that we have an argument for not having the kinetic mixing in the DPU. Okay.
If you
Sorry.
have kinetic mixing, then like this mirror electron is essentially.
That's right. That's right.
You do like
do you mean for a small but not too?
yeah, maybe. I mean, use the kinetic mixing.
Yeah, no. So we haven't looked at this.
Yeah. So
Sorry, I don't.
A lot of these stories mimic what's already been done for twin days.
Yeah.
And so I was going to mention. I mean, so we have some these twins. But also for this diagram here, even before you go to the breaking to the SU3, when you still have the full bubble copy,
Yeah.
then the kinetic mixing is still again like just twin eggs, and then it happens at full 5 loop when it's full.
Oh, really?
Yeah, you can see you can anyways. I'll point you.
No, I think I'm right. Yeah, with one more. Yeah, you're right. I think 5 loops we have something with one big mediator.
Yes.
Okay, good. Okay, yeah, no, we haven't. Good. But yeah, you're right. There's a 5 loop diagram then, but not this guy here. That's right. Okay, let me quickly summarize. So, yeah, okay. I should stress that the solution to strong CP is still valid even if you're not trying to make E prime dark matter. So if you want to evade all those issues, you could just reheat, like push all these guys to high scales and reheat at rather low temperature, and this would not be at all relevant. That was an add-on we wanted to. So if you don't like this inflation story and so on, you can still decouple the two and keep the solution as a parity solution to strong CP. So we were happy to have something that works in some sort of a complete mirror world where all the gauge groups are treated equally. And as I've tried to argue, it lies in this category of UV solutions where you have to have a full-fledged model and understand all the spectra and the symmetry structure and so on to solve the strong CP problem, which may not be the most attractive solution, but I think it's good to explore. First of all, because it's not been explored much. And second, because it relies on some field theory, like some properties of field theory that have to be kept in mind when you think about what the strong CP means. As we said in that model, the loop corrections are very much under control, and so are the non-perturbative corrections from small instantons. We have very few parameter space, which is nice to like really explore the full fin of the model, but we still can get quite different physics in this parameter space. So as I said, we can have colored boson, for instance, as the first accessible signal. And there is some room for a thermal dark matter candidate, which I think is the first one in this class of model, which also is interesting because it comes with possible signals, like from the direct detection, this irreducible direct detection signal, or from companion signals coming from the presence of this loop. Okay, we'll decide. Thank you for your attention. Thank you.
Because I'm still around this afternoon.
Okay, yeah.
Feel free to ask questions. So thank you again.
Thanks. Yeah.
This double copy. Yeah,
Actually, it's the first time I ever thought about the question of Rabo. Oh.
You're into double copies. I see. Yeah. But by the way, though, why can't you use the other Goldstones in the strong dynamics?
We could. We just haven't thought about this very much. I mean, we focused on the cosmology of the case where you have the scalar, and yeah.
Because you could have some Goldstone that could be the